So now we will discuss different methods that are used to balance selection between solution. Now we will discuss methods to balance selection between solution that are fit according to an objective function, and those are contributed to diversity in population based optimization algorithm. First we have distance function. You can see here fyx, that is the minimum distance between x and any element u in y, and fxy, you can see here, this is the minimum distance between y and any element of v in x. This function measures how different two solutions x and y are from each other. Next we have the objective function, that is fx. Here you can see fx, that is the objective function. It will evaluate the quality of solution x. So here we will generate a score, that is the diversification score. So using diversification score function, we will generate the score, and here you can see this is the distance between solution x and the closest solution in the population. Next you can see beta, that is a constant. It controls the trade-off between fitness and the diversity. Then we have the selection proportion. So we have two type of selection done here to select the solution. First, objective function selection. Second, diversification selection. So in objective function selection, from the population, solutions are selected based on their objective function values. Second, in diversification selection, solutions are selected based on their diversification score. Now let's see how it works. First we will calculate the fitness and the diversity score for each solution in the current population. So we will compute the fitness f of x for each solution. Then we will compute the distance to the nearest neighbor in the population. We have distance x, then population. After that we will compute the diversification score hx using this. Then we will perform selection. So we have selection two type for the fitness based, diversity based. Then in fitness based selection, solutions with higher fitness values are selected, and in diversity based selection, solutions with the highest diversification score, which balance both fitness and diversity, they are selected. We can use this approach because this approach balance between exploiting the high quality solution and exploiting diverse solution, because it focuses on the objective function value, and at the same time it is also focusing on the diversity score. So we have proper balance between the high quality solution and exploiting the diverse solution. Now we will discuss how we can enhance the diversification in PSO and prevent premature convergence. Many optimization problems you may see that PSO algorithm often stuck in the local optima, there is premature convergence. So here we will try to prevent the premature convergence in PSO and how we can enhance the diversification in the PSO algorithm. We will implement a diversity measure along with specific strategy for the repulsion and attraction phases. So we have diversity measure. For this we have a common measure of diversity. So we are using here average pairwise distance. So we will calculate here average pairwise distance between the particles. So first, to check how spread out the particles are in the search space. So first we have average pairwise distance. We will calculate the pairwise distance for each particle in the swarm. We will calculate the Euclidean distance between their position. You can see here using this xik and xjk. They are the coordinates of the particles I and j in dimension k. D is the dimension of the problem. Second, we will compute the average distance, that is the average of pairwise distance, to get the diversity measure using this. Diversity is equal to distance. Then we have pairwise distance that we calculated. After that we have repulsion and attraction phases. So in the repulsion phase, our objective is we want to increase the spread of particles to explore new regions of the search space. So we want our particles to explore the entire search space to avoid premature convergence. So here trigger is when the diversity measure is below a given threshold value. So what we can do here we can update the velocity update strategy. So during the repulsion phase we can modify the velocity update rule to encourage the particles to move away from each other. So here you can see updated velocity equation. So repulsion force encourages the particles to move away from each other. So here we can define this. Alpha, there is a constant that will control the strength of repulsion force. Then we have distance between the particles I and j. So this term ensures that particles are pushed away from each other. Then we have attraction phase. Attraction phase, the objective is to improve the convergence by moving the particles toward promising region of the search space. A trigger is when the diversity measure is above another threshold. It means it is higher. During attraction phase, we can use standard PSO velocity update rule. Then with the focus that it will exploit the best position. G is the global best, P is the personal best. So we can update the particles converge to optimal solution by focusing on the best known position. So here we have diversity measure. We can use pairwise. So here we can use pairwise distance between particles. Repulsion phase, we are increasing the spread using repulsion force. So in repulsion phase, we are using repulsion force to increase the particle spread in the search space. In attraction phase, we will use the standard velocity update rule to focus on exploiting the best solution. This strategy can help us to balance between exploration and exploitation phase, and this can enhance the PSO performance and reduce the risk of premature convergence. Next, we have different diversity maintaining strategy in optimization algorithm. So now we have different methods to ensure that population of solution remain buried and avoid premature convergence. So we have different strategy like kernel based method, nearest neighbor, histogram. They can be useful for maintaining the diversity. First we have kernel based method. This is a non-parametric way we can use to estimate the probability density function of a random variable. So objective is here to estimate the density of particle in search space to identify a region with high and low concentration of particles. So what we will do, we will estimate the density of particles. Where particles are high or low, we will identify the regions with high or low concentration of the particle. So this function, so we are using here kernel function, that is the Gaussian, to smooth the density estimate. For each particle, we will compute using this. K is here the kernel function, H is the bandwidth, that is the smoothing parameter, N is the total number of particles. Next we have diversity measure. So we are using a density estimate to access different region of search space with low density of particles and high density of particles. Low density means high diversity, high density of particles means low diversity. So during the repulsion phase, particles can move away from region with high density, and is ensuring better convergence of search space. Next method we have nearest neighbor method. So this method focus on the distance between the particles. So objective is to maintain the diversity by monitoring how close each particle is to its nearest neighbor. So we will check how each particle in the current population is nearest to its neighbor. So method we can use here distance calculation and diversity measure. In distance calculation, for each particle, we will find out the distance between the particle and its nearest neighbor. Second, diversity measure, here we will average this minimum distance across all particles to get a measure of overall diversity. So in PSO algorithm, during repulsion phase, if average nearest distance is below a certain threshold, apply repulsion force to increase the distance and improve diversity. Then we have histogram based method. So we can use histograms to monitor the distribution of particles across different regions of the search space. So using this method, what we can do, we can monitor the particles distribution across different region in the solution space. So first we will divide the search space into grids. Second, We will calculate histogram. We will count the number of particles in each vein. Then we have the diversity measure. We will evaluate the distribution of particles across veins, bins or grids, whatever you can say. So well distributed histogram indicates high diversity, and skewed histogram indicate low diversity. So during repulsion phase, we can apply the adjustment to particles to ensure that they are evenly distributed across the veins, preventing clustering in specific areas of the search space. So using this method, we can prevent the clustering of particles in specific areas of the search space. During the repulsion phase, we can adjust the particles to ensure they are evenly distributed across the grids. Now we have different diversity based indicators which help to maintain a diverse population and avoid premature convergence. First we have spread. Spread measures how well the solution covers the entire range of the objective space. So during calculation, we will determine the extremes. We will find the minimum and the maximum value for each objective in the solution set. Second, we will calculate the spread. So we calculate the range of each objective, and then we will find the total spread as the sum or the average of these range. Using this formula, here we have y max and y min that represent the maximum and the minimum value of the objectives across all solution. M is the number of objectives. Done. So we'll find out the maximum and the minimum values of each objective in the solution set. Then we'll compute the range of each objective and then find the total spread as the sum or average of these range. Next diversity based indicator, we have spacing that measure the uniformity of distribution of solution. It evaluates how evenly the solution are spaced along the Pareto front or in the objective space. So first we will sort the solution based on their objective values. Second, we will compute the distance. So we will calculate the distance between each pair of solution. Third, we will compute the average distance and compare it with ideal spacing. Using this formula, di, that is the distance between the solutions, and d ideal, that is the ideal distance between solution. Next we have entropy. So entropy is used to measure the diversity of solution. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.